In this video, we're going over section 3.5, which is titled The Mole, Counting Atoms and Compounds. In this section, we are going to learn how we look at molecules or atoms in terms of units of measurements. So it is important to note that small particles such as atoms and molecules, we count them using a special unit, which is called the mole. The mole as a unit is also known as Avogadro's number. And it establishes that if you have Avogadro's number, in other words, 1 mole of a substance is going to equal 6.022 times 10 to the 23 items. So that is an established equality. In the image that you see in the bottom of the slide, these images are representing 1 mole of each one of those elements. Here we have 1 mole of zinc, 1 mole of carbon, 1 mole of magnesium, 1 mole of copper. One of my favorite stores to go shopping is actually Trader Joe's. And it is interesting to see that when you look at its packaging for their guacamole, they actually utilize the picture of the person that did all of the investigations for the concept of the mole. You can see that the image that we have on the left side of the packaging for the guacamole from Trader Joe's. So right there you see in a bubble that it says, "Let's party arriba." That is actually Avogadro. And that's the Italian scientist that did the investigation in order for us to have a unit to count atoms and molecules. The first thing that we're going to do is actually to understand how we can utilize Avogadro's number to count atoms. So the first conversion that we're going to learn in this concept is if we are given moles, and it could be moles of an element or moles of a compound, how can we obtain atoms or molecules respectively? So you can see here that this double-headed arrow is kind of representing the flow of work that is going to be utilized in order to, in the top equality, to go from moles of element to atoms of that element. You can also utilize it for ions, but we are not going to be utilizing it specifically for ions. Avogadro's number is going to be the conversion, in other words, the equality that we will be utilizing in order to convert from one unit to the other. As I just mentioned, when it comes to Avogadro's number, it says that 1 mole equals 6.022 times 10 to the 23rd items. The items, when you start from an element, is going to be specifically atoms. So you will be observing that if you're given moles of an element and you need to convert to something, those items are going to be specifically atoms. Now, when it comes to moles of compound, and you need to convert it to molecules or formula units, we are not going to be utilizing formula units. You also use Avogadro's number. Now, it is important to note that depending on the direction of the conversion that you're doing, you may have to multiply by Avogadro's number, or you may have to divide by Avogadro's number. So the idea is that if you're given moles, and since we are going to cancel units diagonally because of dimensional analysis, if you're given moles and you need to find atoms, so you're going in this direction, what you're going to do is multiply by Avogadro's number. In the case that you're given atoms and you need to find moles of an element, meaning that you're going in this direction, then you will be dividing by Avogadro's number. The same process would happen if you start with compounds. If you start with moles of a compound and you need to convert to molecules of that compound, understand that you will be multiplying by Avogadro's number, and vice versa. If you start with molecules of a compound and you need moles, understand that you will be dividing by Avogadro's number. Let's do a couple of examples so we can solidify this concept. The following problem reads, how many CO2 molecules are in 0.50 moles of CO2? So the unit given in this problem is that we're going to start with 0.50 moles of CO2. That means that if we relate it to the two different flowcharts that we have here, we are given specifically moles of compound. We are trying to find molecules. So we are going in this direction. So we land here. So that means that in this case, we're going to multiply by Avogadro's number. So Avogadro's numbers equality, what we're going to do is set it up as a fraction. Where in the bottom, I'm going to say 1 mole of CO2. And on the top, what it equals to, which is 6.022 times 10 to the power 23. Our items are going to be molecules of CO2. So when it comes to this, make sure that you know how to enter numbers that are in scientific notation into your calculator. So when I multiply 0.5 times 6.022 times 10 to the 23rd, my calculator display shows 3.011 times 10 to the 23rd. Now, because the measurement given has 2 sig figs, I need to round this value to 2 significant figures. So that means that my calculator display will convert to 3.0 times 10 to the 23rd molecules of CO2. Because remember, overall, the moles of CO2 will cancel with the moles of CO2. And all we have to do is multiply 0.5 times 6.022 times 10 to the 23rd. And that's how we obtain the result. In the bottom of the slide, you can see that we also have 2 problems. I'm going to do specifically problem 4. As you can see in problem 4, it reads, how many moles of carbon are in 7.46 times 10 to the 23rd atoms of carbon? So in this case, if I relate it to what I have here, I am given atoms of an element and I need to convert to moles of an element. And when I'm going in this direction, as you can observe, I'm going to divide by Avogadro's number. So let me set up the problem. I'm going to write the measurement given, 7.46 times 10 to the 23rd atoms of carbon. And then to get to moles of carbon, what we're going to do is that we're going to divide by Avogadro's number, 6.022 times 10 to the 23rd atoms of carbon. And that equals to 1 mole of carbon. When I cancel my units, atoms of carbon will cancel with atoms of carbon. So overall, my result is going to be in units of moles of carbon. And when I divide these 2 values, 7.46 times 10 to the 23rd, and I divide it by Avogadro's number, 6.022 times 10 to the power 23rd, I observe that my calculator display is 1.23879, and there's more digits there. So I need to round my calculator display to 3 sig figs because that's the coefficient. given in my scientific notation for the unit or the measurement that is given. And when I round my calculator display to 3 significant figures, this is 1.24 moles of carbon is what is obtained. Make sure that you practice the other problem that you see on the slide. Now that we know how to convert between moles, atoms, or molecules, let's observe how this also relates to molar mass. So in the examples that we were just performing a few moments ago, we were converting from moles. It could be of an atom, it could be meaning an element, or it could be a compound. We were able to convert to atoms. Now, it's important to note that moles also has an equality to units of grams. We can observe that, for example, in the case of carbon, we can have observed that in this top loading balance, this is measuring specifically 1 mole of carbon. And 1 mole of carbon is exactly 12.01 grams. Now, that value of 12.01 grams, it is something that if you pay close attention to the periodic table, you may have seen it before, because this is actually the atomic mass for the element. Now, we first learned that that atomic mass will have units of AMU, but there's also another additional interchangeable unit that can be utilized. So AMU is the same thing as saying grams in 1 mole. So we can actually say that the atomic mass for an element, is also given in grams per 1 mole. So when it comes to this, let's understand that since the atomic mass is given in units of grams per mole, we can actually calculate the molar mass of any element or compound for that matter, since we will have those units that will allow us to convert between grams and moles for any element or compound. So let's actually see how those conversions are actually performed. In order to do that, let's understand that there's a particular transition that is going to happen. If we are given specifically grams of an element, we can convert to moles of an element. Our conversion factor is going to be the molar mass for that element. And remember that that comes from the periodic table. If we are given grams of a compound, like the example that we're about to do, you have to calculate the molar mass for that compound, and then you are going to be able to convert to moles of a compound. As you can see, this is not only in one direction, you can go from grams to moles and vice versa, from moles to grams. Now, if we are given specifically grams of an element or a compound, and then we need to convert to moles, meaning that we're going in this direction, understand that we're going to divide by the molar mass of that element or that compound. And that has to do with, in dimensional analysis, we specifically will be canceling units. So since grams are given and it's going to go in the bottom, that's why we are going to divide by the molar mass. But if you're given moles and you need to find grams of an element or grams of a compound, so if we're going in this direction, understand that in order to do this, we are going to specifically multiply by the molar mass of an element or a compound. Let's actually do an example so we can illustrate this process. The example that we have here on the slide states a box of table salt in other words, NaCl, contains 737 grams of NaCl, or in other words, sodium chloride. How many moles of sodium chloride are in the box? So in order to start this problem, first we have to state what is the measurement given, which is going to be 737 grams of that sodium chloride. We know that our conversion factor is going to be the molar mass of our compound, because that's what we're working with, a compound. That has not been given in the problem, and it can be calculated. This is how you calculate the molar mass for a compound. Our compound is composed of sodium and chlorine. We can observe that there is no subscript, specifically in sodium chloride. So we are going to assume that they have a subscript of 1 because we learned before that when there is a subscript of 1, that value is omitted. So when this happens, then we can say, well, in sodium chloride, I'm going to first establish what is the subscript that each element has. We have 1 sodium, we have 1 chlorine, and then we're going to multiply that subscript specifically by the molar mass for that element. So when we do that, let's write down the molar masses for sodium and for chlorine. Sodium, if I round it to 2 decimal places, and I'm just utilizing a simplified periodic table that I'm utilizing, but you should utilize all the numbers that are given in the periodic table that will be provided for you during examinations. Sodium, if I round it to 2 decimal places, like in the periodic table that I'm using, its atomic mass is 22.99, and that's grams per mole. Chlorine, on the other hand, has a molar mass of 35.45 grams per mole. So for this calculation, since I'm multiplying by 1, let's establish that is going to equal the same value of the atomic mass for each corresponding element. So here I have 22.99 grams per mole that are contributed by the sodiums that I have in my chemical formula, 35.45 grams per mole contributed by the chlorine that I have in the formula. Remember that if you have larger subscripts for the compound that you're working with, then that needs to take into account by multiplying the subscript by the molar mass. And in this case, is only 1. Once you have obtained those results, you're going to add those 2 molar masses for each of the elements that are in the periodic table, or in this chemical formula, I should say. So we have 22.99 added to 35.45. So we see that the molar mass for sodium chloride is 58.44 grams per mole. Now that we have the molar mass, in this case, since we are going from grams to moles, we are going to divide by the molar mass. So what that means is that in this fraction that I have, in the bottom, I'm going to put 58.44 grams, and on the top, 1 mole. Remember that the units are specifically for sodium chloride. So once I have that, the units of grams of sodium chloride cancel with each other. My resulting unit is going to be moles of sodium chloride. And when I take 737 and I divide it by 58.44, I see that my calculator display is 12.611, and there's a series of digits, but I must round to 3 significant figures because that's what was given to me. So when I do that, I'm going to round my calculator display to 3 sig-figs. So this corresponds to 12.6 moles of sodium chloride. I'm going to repeat the calculation to make sure that what I plugged in was correct. And that's the result that I get. Now, in the next slide, we can see that we have a series of practice problems for us to specifically understand how this process goes when we are given grams of an element to moles of an element, or grams of a compound to moles of a compound, and vice versa. So in order for me to illustrate how to do these conversions, I'm going to do specifically problem 2. As you can see, problem 2 states, given 0.345 moles of chlorine gas, how many grams would you have? One of the things that you need to remember is that there are a list of elements that actually are molecular elements. What that means is that we usually find them as diatomic elements, meaning that we find the element and it has a subscript of 2. Chlorine gas is one of those. So when we are talking about chlorine gas, this refers to Cl2. It's not going to be just Cl. So we are talking right here about the diatomic form of chlorine. Other elements that also have this are going to be hydrogen, which is mostly found as a gas, nitrogen, oxygen, fluorine, chlorine, as you can see in the example, bromine, and iodine. It's important to note that out of all of these 7 diatomic compounds, most of them are gases. The only ones that are not is bromine, which is usually a liquid, and iodine, which is usually a solid. So if you see a problem that it says solid iodine, assume I2. If you see a problem that says bromine liquid, understand that it's referring to Br2. So let's just go over this problem. So we are given the measurement of 0.345 moles of Cl2. In this case, we are given moles of a compound, or a diatomic element for that matter. And then we are going to convert to grams of that compound or diatomic element. So when we are doing that, remember that we are going to specifically multiply by the molar mass. So to find the molar mass of Cl2, I have to say, well, for my chemical formula, I have 2 chlorines. And since the molar mass, or in other words, the atomic mass of chlorine is 35.45 grams per mole, that means that for this diatomic element, when I multiply 35.45 times 2, that shows that specifically Cl2 has an atomic mass of 70.90 grams per mole. So with this information, if I'm trying to find how many grams I have in this measurement, I'm going to place in the bottom 1 mole of Cl2. And on the top, I'm going to put 70.90 grams of Cl2. In terms of units, the moles of Cl2 will cancel with the moles of Cl2. So my resulting unit is grams of Cl2. So I'm going to take 0.345 and multiply it by 70.90. My calculator display shows 24.4605 as my result. But since I'm given 3 significant figures, I need to round that calculator display to 3 significant figures, which means that my final answer is going to be 24.5 grams of Cl2 are present in 0.345 moles of Cl2. When it comes to problems between moles and grams, understand that. Make sure that you practice the following problems that you have on the slide. Now that we know how to go between atoms and moles, and even moles to grams, we can perform those conversions if we're giving any of the two ends that I mentioned verbally. Let's actually observe how that is. So in this path, we can observe that we can go from grams of an element to moles of an element and all the way to atoms. We can go from grams of a compound to moles of a compound to molecules of a compound. The two conversion factors that we learned previously, molar mass and Avogadro's number, is what it is utilized. So I want you guys to take a moment and predict what's going to be the mathematical operation in order for you to accomplish going from grams all the way to atoms, or going from grams of compound all the way to molecules. So if you predicted that if I'm going in this direction from grams of element to moles of element, that you divide by the molar mass, you're correct. If once you have moles of an element, you're going to then multiply by Avogadro's number, you are correct. If we are doing the reverse, going from atoms to moles, we're going to divide by Avogadro's number. And if you have moles and you need to find grams, you are going to specifically multiply by the molar mass of that element. So the same operations can be applied to grams of compounds to go to molecules or vice versa. So let me just write that in. As we go in this direction, we are going to divide. Here we're going to multiply, and the reverse means that we're going to divide. And here we're going to multiply. Let's do one application problem so we can see specifically this at work. So I'm going to specifically do problem number 1, which reads, how many grams of magnesium are in 3.01 times 10 to the 22 atoms of magnesium? So in this problem, specifically, I am given atoms of an element, and I need all the way here, I need to find grams of that element. So first, I'm going to write the measurement given, which is 3.01 times 10 to the power 22 grams, and the symbol for magnesium is Mg. I know that I have two conversion factors. Since I'm going from atoms all the way to grams, my first conversion factor is going to be Avogadro's number. So I'm just going to write a note here that here we have Avogadro's number. as my conversion. And then in the next one, we are going to use molar mass as the conversion factor. Now, we are first going to divide by Avogadro's number. So that means that we're going to put in the bottom. Let me fix the units. Because it was incorrect to put grams. Atoms is the correct unit that was given to us. We are going to do 6.022 times 10 to the 23rd atoms of magnesium in 1 mole of magnesium. So that means that we already covered the first conversion factor. And in the next one, we have to multiply by the molar mass. So that establishes that in the bottom, I'm going to do 1 mole of magnesium. And on the top, I'm going to put the molar mass of magnesium. If I round it to 2 decimal places, it's going to be 24.31 grams of magnesium. So when I do this, atoms of magnesium cancels with atoms of magnesium. Moles of magnesium cancels with moles of magnesium. The overall unit for my measurement is going to be grams of magnesium. And to complete this problem, I'm going to do 3.01 times 10 to the 22nd power. I'm going to multiply that by 24.31. And all of that, I'm going to divide by 6.022 times 10 to the 23rd power. So I get a calculator display of 1.21509, and there's a series of digits after that. But because I started specifically with 3 significant figures in the coefficient for the scientific notation for the atoms of magnesium, I need to round my result to 3 significant figures. So my final answer is 1.22 grams of magnesium. Let me redo the calculation to ensure that I enter it correctly in my calculator. 3.01 times 10 to the 22nd times 24.31. I divide that by 6.022 times 10 to the 23rd, and I obtain the same result. Make sure that you practice the other problem that we have on the slides.